Hello, and welcome to a new video. Today we will discuss feature processing in LightAutoML. On this slide, you can see a high-level scheme of LightAutoML. We start with taking raw data, which is commonly a pandas data frame, and selecting a task to solve, regression or classification. These instances proceed to a reader object, which is responsible for converting data into inner LightAutoML format and generating cross-validation splits. Then, the data goes into several levels of ML pipelines. Each ML pipeline consists of a feature processing block and ML algorithms with optional hyperparameters tuners. Zero-level models take only data features as inputs, while upper-level models take both data features and previous-level model predictions, implementing a stacking ensemble. Finally, last-level predictions come in a blender, which combines the outputs and generates a final prediction. TabularAutoML is a special preset designed for processing tabular data. It supports numeric, categorical, and date features. TabularAutoML uses two types of ML algorithms, a linear model with L2 regularization and a gradient boosting in LightGBM and CutBoost libraries implementations. LightAutoML supports a great variety of losses and metrics to select the best model. The losses include log loss for binary classification, cross-entropy for multi-class classification, and many popular options for regression, for example, mean squared error or mean absolute error. Besides common metrics like ROCAUC or R-squared, the users can specify their own custom metric for optimization. First things first, we have to specify roles for features in the dataset. The only required role is target, the column we want to predict. Other possible roles are numeric, category, and date time. If not provided, they will be determined automatically using auto-typing. The text role, used for raw text, is common in a NLP preset. As I mentioned earlier, the reader object can do auto-typing. There are two possible approaches. The simple approach is based on a data format. If the feature can be converted to a date, then it is probably a datetime role. If the feature looks like a number, then a numeric role is assigned. Otherwise, the feature is a category. The advanced approach, in turn, selects between numeric and category roles based on some statistics. It also offers the best pre-processing option for the feature. A common way to process dates is to extract seasonality, like month or weekday, and process it as a category. Another option is to calculate the difference with the base date, which is defined by the user. Processing numerical features for linear models includes normalization, with subtracting mean and dividing by the standard deviation of the feature, filling missing values with a median, adding a flag if the feature is missing, or feature discretization. The latter may be especially useful if the missing values are filled with an out-of-range value, like shown in this plot. If our feature is a probability, which is specified by the user or being an output of the previous level model, then the log odds is calculated. There are also 5 types of encoding for categorical features. Label encoder is used for the models which can handle categories directly, or for the trees if the number of categories is not too large. One-hot encoder is good for linear models, while LightAutoML uses label encoder. In fact, in implementation, the transform is equivalent to one-hot encoder. Ordinal encoder might be useful for ordered categories, for instance, for grades. Frequency encoder will come in handy for features with rare categories. And target encoder is a mean value of target over the category regularized with a prior. This one needs to be calculated out of fold in order to prevent target leak. For each training fold, we compute the regularized mean target over the rest of the folds. For test objects, we use the value estimated on the whole training set. The regularization coefficient alpha is also fit using cross-validation. As for the advanced typing, the feature role is determined by its encoding, which predicts the target the best. Overall, 4 types of encoding are considered. Raw encoding and the composition of binning and target encoder vote for the numeric role, while target encoder and frequency encoder vote for the category role. Normalized Gini coefficient between the encoding and the target is used as a quality score. This metric is similar to ROC-AUC and shows us if the encoding helps us to sort the target. The resulting feature role is determined based on a bunch of rules, such as the raw score is maximal or the bin score is maximal, while the raw score is the second largest. The parameters of these rules may be configured, though the default ones usually perform well. It is also possible to turn off advanced typing, because in some experiments held by the developers of LightAutoML, it appeared to perform slightly worse than the simple typing. Now, let's discuss feature selection in LightAutoML. There are two stages of feature selection, before and after the feature extraction, pre-selection and post-selection respectively. The latter is not used in the TabularAutoML preset. Three pre-selection strategies are available: no selection, selection based on feature importances, and forward selection. A gradient boosting model is used to estimate the importances. There are two available approaches: feature importance and permutation importance. The former utilizes the following idea: the more splits are made on a given feature, the more important it is. The latter proposes to shuffle each feature in the sample and see how much the predictions of the model have worsened because of this permutation. Both approaches preserve the features with an importance over some threshold. This threshold equals 0 by default, so we take only those features which do not deteriorate our model. Overall, the selection is fast and conservative, meaning that only a small share of features is dropped. Another strategy is forward selection, which works on top of permutation importance. All features are sorted by the value of permutation importance. Then we add blocks of features iteratively and retrain the gradient boosting on all added features. These iterations continue until the model quality stops improving. The rest of the features are dropped. Such selection is rather slow, as we need to train gradient boosting several times. However, this method allows us to select a small subset of the most significant features. Unfortunately, the resulting model quality is never better than after applying the feature importance method, but it might be extremely useful if we are aiming at a model with a fast inference. In this video, we have discussed different approaches to feature processing and feature selection in LightAutoML. Thank you for your attention.